Welcome to Nap Through Universe. Get comfortable for this new journey. Close your eyes, relax, and enjoy this journey. Imagine a world without a sun. No sunrise, no sunset, no seasons, just eternal night stretching across billions of years. The temperature on this world hovers near absolute zero, minus 270 degrees Celsius. The sky is black, punctuated only by the faint light of distant stars that will never grow brighter. No moon rises, no dawn breaks. This planet drifts through interstellar space, alone, frozen, silent. This isn't science fiction. These worlds exist, billions of them. They're called rogue planets, worlds cast out from their solar systems, condemned to wander the void between stars forever. Orphaned from their parent stars, they travel through darkness for eons, carrying with them the memory of warmth they will never feel again. In 2011, astronomers made a startling discovery. While surveying a patch of sky toward the galactic center, they detected rogue planets through gravitational microlensing. Not dozens, not hundreds. Statistical analysis suggested something extraordinary. There might be more rogue planets in our galaxy than stars. 2 trillion stars light the Milky Way. If rogue planets outnumber them, there could be trillions of these dark, silent worlds drifting through the cosmic void. Entire solar systems worth of planets expelled into darkness, forming an invisible population we're only beginning to detect. What forces eject planets from their solar systems? Could life survive on a world without a star? Are there rogue planets passing near our solar system right now, invisible in the darkness? Today, we journey into the cold and the dark. We explore the loneliest worlds in existence, planets that will drift through space long after every star has died. Prepare yourselves. We begin. For most of astronomical history, planets were defined by their relationship to stars. A planet orbits a sun. Without that orbit, without that gravitational anchor, it's not really a planet. Or so we thought. The first hints that rogue planets existed came not from direct observation, but from computer simulations of solar system formation. In the 1980s, astronomers modeling how planetary systems form discovered something unsettling. The simulations showed that gravitational interactions during the chaotic early days of a solar system frequently eject planets into interstellar space. Not occasionally, frequently. Sometimes half the planets initially formed around a star get thrown out. The process is violent. Multiple protoplanets, planetary building blocks, form in the swirling disk of gas and dust around a young star. As they grow through collisions and accretion, their gravitational fields begin to affect each other. Orbits shift. Planets migrate inward or outward. Sometimes 2 planets pass close enough that their gravitational interaction becomes a 3-body problem, one of the most chaotic scenarios in celestial mechanics. One planet gains energy and moves to a more distant orbit. The other loses energy and spirals inward. But there's a third possibility. One planet gains so much energy that it exceeds the escape velocity of the entire solar system. It breaks free from the star's gravitational grip and is flung into interstellar space at tens of kilometers per second. The ejected planet carries with it whatever momentum the interaction provided. It becomes a rogue, a wanderer with no home, drifting through the galaxy on a trajectory that will never return to any star. Early simulations suggested this happened to perhaps 10% of planets. Later, more sophisticated models revised that estimate upward, way upward. Detecting rogue planets presented an enormous challenge. These worlds emit no light of their own. They reflect no starlight. They're too far from any star. They're invisible black spheres drifting through black space. But gravity bends light, and where there's gravity, there's a way. Gravitational microlensing occurs when a massive object passes between Earth and a distant star. The object's gravity acts as a lens, bending and magnifying the star's light. For a brief time, hours to days, the background star brightens, then returns to normal as the lensing object moves on. In 2006, the Optical Gravitational Lensing Experiment, OGLE, and the Microlensing Observations in Astrophysics collaboration began detecting microlensing events that didn't fit the pattern of stars or stellar remnants. The events were too brief. The lensing masses were too small. These were planet mass objects, but there was no evidence of a parent star. They were alone. By 2011, the data was undeniable. A team led by Takahiro Sumi analyzed microlensing surveys covering 50 million stars toward the galactic bulge. They detected 10 Jupiter-mass objects with no associated star within 10 astronomical units, the distance from the Sun to Saturn. Statistical analysis led to a stunning conclusion. For every star in the Milky Way, there are approximately 2 Jupiter-mass rogue planets. Given 200 billion stars in our galaxy, that means 400 billion rogue planets the size of Jupiter or larger, drifting unseen through interstellar space. But that was just the beginning. The survey was only sensitive to large planets. Smaller rogues, worlds the size of Earth, Mars, or smaller, remained undetected. If you include those, the numbers explode. Some estimates suggest there could be trillions of rogue planets in the Milky Way, more rogue worlds than planets orbiting stars, more orphans than children with homes. The galaxy is far more crowded than we thought. We just can't see most of its inhabitants. How does a planet get ejected from its solar system? Several mechanisms can cast a world into darkness. The most common involves planetary migration during system formation. When multiple gas giants form in a young solar system, their gravitational interactions can become unstable. Orbital resonances amplify perturbations. Planets play gravitational billiards, exchanging energy and angular momentum. Computer simulations by Hal Levison and colleagues at the Southwest Research Institute showed that in systems with multiple Jupiter-sized planets, at least one gets ejected in about 30% of cases, sometimes two. Occasionally, the entire planetary system tears itself apart, leaving only one or two survivors in stable orbits. Our own solar system might have ejected planets. Some models of the early solar system include a fifth gas giant, a planet that formed between Saturn and Uranus, but was ejected when Jupiter and Saturn underwent orbital migration about 3.8 billion years ago during the late heavy bombardment. If true, somewhere in interstellar space, there's a planet that once orbited our Sun, a former sibling of Earth, cast out into eternal cold. Another ejection mechanism involves stellar encounters. When two stars pass close to each other, common in the crowded environments of young star clusters, their gravitational fields can strip planets from each other's systems. A star passing within a few hundred astronomical units of our solar system could perturb the orbits of outer planets enough to eject them. In the dense cores of globular clusters, where stars are packed thousands of times more tightly than in our neighborhood, this happens frequently. Binary star systems present their own challenges. About half of all stars exist in binary or multiple star systems. Planets in such systems occupy complex gravitational landscapes. Certain orbital configurations are stable, but many are chaotic. Planets in unstable orbits eventually get ejected or crash into one of the stars. Finally, supernovae can eject planets. When a massive star explodes, any planets in the system experience a sudden decrease in gravitational binding as the star loses most of its mass. Planets that were in stable orbits suddenly find themselves moving too fast for their new gravitational environment. They drift away, becoming rogues associated with supernova remnants. Each mechanism contributes to the rogue planet population. The galaxy has been forming stars and planets for over 10 billion years. Ejection events have accumulated across cosmic time, populating interstellar space with these dark wanderers. In 2007, microlensing surveys detected an event designated MOA 2007 BLG 192L. The lensing signature indicated a planet roughly 3 Earth masses, a super-Earth, with no star detected within 10 astronomical units. This was significant. Previous detections had focused on Jupiter-mass rogues. This object was much smaller, suggesting that rogue planets spanned the full range of planetary masses, from gas giants down to rocky worlds like Earth. The discovery implied that Earth-mass rogues exist in even greater numbers than Jupiter-mass ones. If planetary formation follows similar mass distributions for rogues as for orbiting planets, with smaller planets more common than larger ones, then for every Jupiter-mass rogue, there might be 10 to 100 Earth-mass rogues. Trillions becomes tens of trillions. Perhaps 100 trillion rogue planets populate the Milky Way, more than 500 for every star. The universe is full of dark, silent worlds. They outnumber the illuminated ones. Most planets exist in darkness, untethered from stars, drifting through voids that span light years. The question becomes not are rogue planets common, but rather, are star-orbiting planets the exception? In 2013, NASA's Wide Field Infrared Survey Explorer, WISE, completed an all-sky survey in infrared wavelengths. While searching for brown dwarfs, objects between planets and stars in mass, the survey detected several candidates that might be rogue planets relatively close to our solar system. One object, designated WISE 08550714, has a temperature of -23 degrees Celsius, barely warmer than Earth's poles. Its mass is estimated at 3 to 10 Jupiter masses, placing it in the planetary range. It's located just 7.2 light-years away, our fourth closest known neighbor after the Alpha Centauri system, Barnard's star, and the Lumen 16 brown dwarf binary. This proximity is telling. If a planetary mass object exists within just 7 light-years, and if that's representative of average rogue planet density, there could be thousands of rogue planets within 100 light-years of Earth. WISE detected the object because despite its cold temperature, it still emits infrared radiation, residual heat from its formation, or ongoing gravitational contraction. Younger rogue planets, ejected more recently, would be warmer and easier to detect. Older ones, cooled over billions of years, would be invisible even in infrared. The survey's detection limit means we're only seeing the tip of the iceberg. For every rogue planet warm enough for WISE to detect, dozens or hundreds of colder, older rogues remain invisible. In 2020, astronomers using the European Southern Observatory's Very Large Telescope surveyed the Upper Scorpius and Ophiuchus star-forming regions. These are nurseries where new stars and planets are currently forming, allowing direct observation of ejection events. The survey identified at least 70 rogue planet candidates with masses between 4 and 13 Jupiter masses. These objects are young, only a few million years old, and still warm from formation, making them detectable in infrared. The density of rogue planets in these regions exceeds previous estimates. For every star forming, the data suggests at least one planetary mass object is ejected. Given that these are young systems where ejection events are still ongoing, this ratio might increase as the systems age and gravitational interactions continue. Perhaps most intriguingly, several of the detected rogues showed evidence of circumplanetary disks, rings of gas and dust orbiting the planets, similar to the disk around Saturn, but vastly larger. These disks could potentially form moons. The implications are profound. Rogue planets might host their own moon systems. A rogue planet with a large moon, particularly if the moon is tidally heated by gravitational interactions with the planet, could potentially harbor liquid water, despite being light-years from any star. In 2021, analysis of data from the Gaia spacecraft, which is mapping the positions and motions of over 1 billion stars with unprecedented precision, suggested that several nearby objects previously classified as brown dwarfs might actually be rogue planets. Statistical analysis of Gaia's parallax measurements indicates that there is a 90% probability of at least one rogue planet larger than Neptune within 10 light-years of Earth. There might be one within 5 light-years, closer than Alpha Centauri. This planet would be completely invisible to optical telescopes. It wouldn't reflect sunlight. There's no nearby star to illuminate it. it would emit only faint infrared radiation, cooled over billions of years to temperatures near absolute zero. It could pass within the orbit of Pluto, just 40 astronomical units from the Sun, and we might not notice unless we were specifically looking for it. Its gravitational influence on outer solar system objects would be subtle, perhaps misattributed to other causes. The Vera Rubin Observatory, scheduled to begin full operations in 2025, will conduct the Legacy Survey of Space and Time, imaging the entire visible southern sky every few nights for 10 years. Its sensitivity to very faint objects might detect nearby rogue planets through their motion against the background stars. If a rogue planet passed within a few light years, Rubin might catch it. We'd see it move, a dark object revealed only by occultation, blocking background stars as it drifted across our line of sight. The James Webb Space Telescope, launched in 2021, has infrared sensitivity that could detect warm rogue planets within a few hundred light years. Its coronagraphic instruments, designed to block bright stars and image faint companions, might image rogues that are still cooling from their formation. In 2023, JWST began a program targeting nearby young star-forming regions, searching for rogue planets using mid-infrared imaging. The data will take years to analyze fully, but preliminary results suggest numerous planetary mass objects with no parent stars. One particularly interesting target, a rogue planet candidate in the TW Hydrae Association, roughly 150 light-years away. The object appears to have a mass around 5 Earths and shows spectroscopic evidence of water vapor in its atmosphere. Water vapor on a rogue planet might seem impossible. Any water should be frozen solid at interstellar temperatures. But if the planet has significant internal heat from radioactive decay or residual formation energy, subsurface oceans could exist beneath thick ice shells. This is similar to how Jupiter's moon Europa and Saturn's moon Enceladus maintain liquid water oceans beneath their frozen surfaces, heated by tidal forces and radiogenic decay. A rogue planet wouldn't have tidal heating from a parent star, but radiogenic heating could persist for billions of years. The possibility of liquid water on rogue planets opens extraordinary questions about habitability in the absence of stars. What would the atmosphere of a rogue planet be like? For gas giants like Jupiter, ejection wouldn't fundamentally change atmospheric composition. The planet would retain its hydrogen and helium envelope. Temperature would drop as the planet radiated away its formation heat, but the atmosphere would remain. Over billions of years, the upper atmosphere would cool to near absolute zero. Hydrogen and helium would remain gaseous. Their condensation temperatures are only a few degrees above absolute zero, but any heavier gases, methane, ammonia, water vapor, would condense and rain out, forming icy clouds that settle into the planet's interior. The result? A gas giant with a cold, transparent upper atmosphere and deeper layers where complex chemistry continues, powered by residual internal heat. Rocky rogue planets present a different scenario. Earth-like worlds ejected from their parent stars would undergo catastrophic cooling. Within a few million years, the atmosphere would freeze and fall as snow. First, water vapor would condense, covering the planet in a global ocean. Then that ocean would freeze into ice kilometers thick. Next, carbon dioxide would condense, forming dry ice that buries the water ice. Finally, nitrogen and oxygen would liquefy and freeze, creating a thin veneer of molecular ice covering the entire surface. The planet would become a frozen sphere, its atmosphere reduced to a solid layer perhaps tens of meters thick. Beneath that frozen atmosphere, beneath kilometers of ice, if the planet retained significant radiogenic heat, a subsurface ocean might persist. Could life exist on a rogue planet? On Earth, nearly all life depends on photosynthesis, organisms capturing sunlight to produce energy. Remove the sun, and photosynthetic life dies within days. Food chains collapse. Within years, Earth's surface would be frozen solid, the atmosphere compressed into ice. Life as we know it would end. But there are exceptions. Deep-sea hydrothermal vent ecosystems don't depend on sunlight. They derive energy from chemical reactions, chemosynthesis. Microbes oxidize hydrogen sulfide and methane seeping from Earth's crust, forming the base of food chains that include tube worms, crabs, and fish that never see the sun. These ecosystems exist in total darkness, sustained by Earth's internal heat. They demonstrate that life doesn't require starlight, it requires energy gradients. A rogue planet with active geology could host similar ecosystems. If the planet has a liquid water ocean beneath an ice shell, and if geological activity drives hydrothermal circulation, chemosynthetic life could thrive. The required conditions aren't even extreme. A planet with Earth's composition, ejected from its parent star, would retain radiogenic heat from uranium, thorium, and potassium decay for billions of years. This heat flux could maintain a subsurface ocean indefinitely. Add tidal heating from large moons, and the energy budget increases further. A rogue planet with a moon system might have more energy available for life than Europa or Enceladus have in our solar system. And those moons are considered prime candidates for extraterrestrial life. The implications are staggering. If life can exist on rogue planets, and if rogue planets outnumber star-orbiting planets by a factor of 10 or more, then most life in the galaxy might exist on worlds in eternal darkness, beneath frozen surfaces, in oceans that will never see a sunrise. Life might be common in the galaxy. We're just looking in the wrong places. We're searching near stars, but life might thrive in the spaces between. Advanced civilizations might deliberately create rogue planets or exploit existing ones. A sufficiently advanced society could use stellar engines, megastructures that harness a star's energy to generate thrust, to slowly push a planet out of its orbit. Over millions of years, the planet could be ejected, taking with it a civilization sealed beneath artificial domes or underground habitats. Why would anyone do this? To escape a dying star. Red giants eventually consume their inner planets. Ejecting a planet before that happens would preserve the world and its inhabitants. Or to travel. A rogue planet, given sufficient initial velocity, could traverse the galaxy over hundreds of millions of years. It's an interstellar ark, a generation ship on a planetary scale. The planet's internal heat would provide energy for millions of years. Nuclear fusion reactors could extend that indefinitely. The civilization would be self-sufficient, carrying its entire biosphere through interstellar space, visiting other star systems on timescales incomprehensible to us, but routine for a patient species. Some scientists have proposed searching for technosignatures on rogue planets, artificial heat signatures, radio emissions, or atmospheric compositions indicating industrial activity. If civilizations exist on rogue planets, they might be detectable through infrared excess, a planet warmer than it should be given its age and mass, heated by artificial energy production. This would revolutionize SETI. Instead of focusing on stars, we'd survey the darkness between stars, looking for anomalous infrared sources that might be inhabited rogues. Could a rogue planet enter our solar system? Yes. In fact, it's inevitable, given enough time. The Milky Way's stellar density means that stars and rogue planets pass within a few light years of the Sun every few million years. Occasionally, every few 100 million years, an object passes much closer. Computer simulations by the Armagh Observatory calculated the probability of a rogue planet entering the inner solar system. Over the Sun's remaining 5 billion-year lifespan, there's roughly a 10% chance of a Jupiter-mass rogue passing within the orbit of Neptune. Such an encounter would gravitationally perturb the outer planets. Neptune and Uranus could have their orbits altered. Kuiper belt objects would be scattered, some falling inward toward the inner solar system, potentially triggering a new bombardment of Earth. If the intruder passed within 10 astronomical units, the orbit of Saturn, the effects would be more severe. Jupiter's orbit could shift slightly. That small shift would propagate through orbital resonances, affecting Mars and possibly Earth over millions of years. A truly catastrophic scenario, a rogue planet passing within 1 astronomical unit, Earth's orbital radius, is extraordinarily unlikely, with probability less than 1 in a billion over the solar system's remaining lifespan. But in a galaxy with trillions of rogues and hundreds of billions of star systems, it's happening somewhere right now. Some mass extinction events on Earth remain unexplained. The Ordovician extinction 450 million years ago, the Devonian extinction 375 million years ago, both show patterns consistent with environmental disruption but lack clear triggers. Could a rogue planet passing through the outer solar system have scattered comets inward, triggering impact events and climate disruption? The evidence is inconclusive, but the possibility can't be dismissed. The darkness between stars isn't empty. It's populated by countless worlds, most of them invisible, drifting in silence. Some might harbor life, some might host civilizations, and some might eventually come close enough for us to see. Not all rogue planets are ejected from solar systems. Some might form in isolation. In dense regions of molecular clouds where stars are born, gravitational collapse can occur on scales too small to form stars. If a clump of gas and dust has sufficient mass to collapse, a few Jupiter masses or more, but insufficient mass to ignite nuclear fusion, it forms a sub-brown dwarf, also called a planetary mass object. These objects form like stars, but end up with planetary masses. They might have accretion disks and even form moon systems. From a physical perspective, they're indistinguishable from ejected rogue planets, but their origins are entirely different. Observations of star-forming regions show that planetary mass objects exist in environments where ejection would be unlikely, isolated regions far from other stars. This suggests some rogues form independently rather than being cast out. The distinction matters for understanding planetary demographics. If rogues predominantly form in isolation, then the planet formation process is even more diverse than we thought. If most are ejected, then planet formation in conventional solar systems is more violent and chaotic than current models suggest. Current data suggests both mechanisms contribute. Perhaps half of rogue planets formed in isolation, while half were ejected. This makes the total population even larger than ejection models alone would predict. Our solar system might have more planets than we can see. In 2016, astronomers Konstantin Batygin and Mike Brown at Caltech presented evidence for a ninth planet, dubbed Planet 9, orbiting far beyond Neptune. Their analysis of orbital patterns among distant Kuiper Belt objects suggested a planet roughly 10 Earth masses exists, at a distance of 400 to 800 astronomical units from the Sun. If Planet 9 exists, it's almost a rogue planet itself, so distant and cold that detecting it has proven extraordinarily difficult. It would take 10,000 to 20,000 years to complete one orbit. But here's a more radical possibility. What if Planet 9 was fully ejected, and what we're seeing is the gravitational aftermath of its departure? When a planet is ejected, it doesn't just disappear. Its gravitational influence leaves a signature in the orbits of remaining objects. Kuiper belt objects perturbed by the ejection would have aligned orbits, exactly what we observe. If Planet 9 was ejected recently, within the last few 100 million years, it could still be relatively nearby, within a few light years. It would be a former member of our solar system, now adrift in interstellar space, slowly receding. Alternatively, Planet 9 might still be there, extremely distant and difficult to detect. The Vera Rubin Observatory might find it within the next decade, or confirm that it doesn't exist, forcing a rethink of what caused the observed orbital patterns. Rogue planets aren't distributed uniformly across the galaxy. Their density varies with location. Near the galactic center, where stars are densely packed, ejection rates are higher. Stellar encounters are more frequent. Planetary systems are gravitationally disrupted more often. The rogue planet density near the galactic core might be 10 times higher than in the galactic disk where we reside. In globular clusters, ancient spherical collections of stars orbiting the galactic halo, the stellar density is thousands of times higher than in our neighborhood. Planetary systems in globular clusters are unstable. Ejection events are constant. These clusters might be almost entirely populated by rogues, with very few planets remaining in stable orbits around stars. Conversely, in the space between galaxies, the intergalactic medium, rogue planet density is essentially zero. Ejection gives planets interstellar velocities, but not intergalactic velocities. Rogues remain bound to their home galaxies, orbiting the galactic center just as stars do, but on independent trajectories. This means rogue planets are part of galaxies' dark matter budget, though only a tiny fraction. A trillion rogues with an average mass of 1 Jupiter mass contributes roughly 0.0002 solar masses per star, about 1/10,000th of a galaxy's stellar mass, insignificant compared to dark matter, but still a previously unaccounted population. Rogue planets aren't distributed uniformly across the galaxy. Their density varies with location. Near the galactic center, where stars are densely packed, ejection rates are higher. Stellar encounters are more frequent. Planetary systems are gravitationally disrupted more often. The rogue planet density near the galactic core might be 10 times higher than in the galactic disk where we reside. In globular clusters, ancient spherical collections of stars orbiting the galactic halo, the stellar density is thousands of times higher than in our neighborhood. Planetary systems in globular clusters are unstable.
Ejection events are constant. These clusters might be almost entirely populated by rogues, with very few planets remaining in stable orbits around stars. Conversely, in the space between galaxies, the intergalactic medium, rogue planet density is essentially zero. Ejection gives planets interstellar velocities, but not intergalactic velocities. Rogues remain bound to their home galaxies, orbiting the galactic center just as stars do, but on independent trajectories. This means rogue planets are part of galaxies' dark matter budget, though only a tiny fraction. 1 trillion rogues with an average mass of 1 Jupiter mass contributes roughly 0.0002 solar masses per star, about 1/10,000th of a galaxy's stellar mass, insignificant compared to dark matter, but still a previously unaccounted population.
What happens when two rogue planets collide? The vastness of interstellar space, collisions are extraordinarily rare. The average spacing between rogues in the galactic disk is roughly 1 light year, the distance light travels in a year. Even with trillions of rogues, collision rates are negligible on human timescales. But over billions of years, collisions occur, and when they do, the results are spectacular. Two Earth-mass rogues colliding at typical interstellar velocities, around 30 kilometers per second, would release energy equivalent to trillions of nuclear weapons. The collision would vaporize both planets, creating an expanding cloud of plasma and debris. This debris would radiate intensely for thousands of years, cooling slowly in the vacuum of space. Eventually, the cloud might gravitationally recollapse, forming a new rogue planet, a second-generation world forged from the remains of its predecessors. Has anyone observed such an event? Not yet. The collision would be visible across interstellar distances as a brief brightening, days to weeks, followed by a slowly fading infrared source. It would look somewhat like a supernova, but much fainter and with a different spectral signature. Infrared surveys might have detected such events without recognizing them. Transient surveys optimized for supernovae might have filtered them out as non-stellar. Future infrared missions specifically searching for such collisions might discover that they occur more frequently than predicted. In 2015, LIGO detected gravitational waves from merging black holes, opening a new window on the universe. Could rogue planets generate gravitational waves? Individually, no. A single planet moving through space produces gravitational waves too weak to detect with current or foreseeable technology. But consider a rogue planet passing close to a black hole. As the planet approaches, tidal forces stretch it. If it crosses the event horizon, it's torn apart, spaghettified, in a process that might generate a brief gravitational wave burst. LIGO and Virgo aren't sensitive to these events, but future space-based detectors like LISA,
laser interferometer space antenna planned for the 2030s might be. LISA will detect gravitational waves at lower frequencies than ground-based detectors, making it sensitive to events involving smaller masses over longer timescales. If rogue planets frequently fall into black holes, and given the number of rogues and the number of stellar mass black holes in the galaxy, this should happen occasionally. LISA might detect dozens to hundreds of events per year. Each detection would provide data on the planet's mass, composition, and fate. We'd learn whether rocky planets shattered differently than gas giants when encountering black holes. We'd measure how often rogues are captured by stellar remnants. Gravitational wave astronomy of rogue planets represents a future frontier, cosmic seismology of worlds in their death throes.
Could a star capture a rogue planet, adopting it into an existing solar system? Yes, but it's rare. The conditions required are precise. A rogue must pass close enough to a star for gravitational capture, but not so close that it crashes into the star. It must have the right velocity. Too fast and it escapes, too slow and it falls in. Often, capture requires a three-body interaction. The rogue passes near a planet already in orbit, transferring energy in a way that leaves the rogue bound to the star while ejecting or perturbing the original planet. Computer simulations suggest that for every 100 rogues passing through a solar system, one might be captured. Given the frequency of close encounters, this means a typical star might capture a rogue planet once every few billion years. Could Earth be a captured rogue? Almost certainly not. Earth's orbit is circular and aligned with the Sun's equator, consistent with formation in a protoplanetary disk. A captured planet would have a highly elliptical or inclined orbit. But some exoplanets show bizarre orbital properties, retrograde orbits, where the planet orbits opposite the star's rotation, or extreme inclinations. These might be captured rogues rather than planets that formed in place. The star HD 20782 has a planet with one of the most elliptical orbits ever observed, eccentricity of 0.96, meaning it swoops from 0.06 AU to 2.5 AU each orbit. This could be a captured rogue that's been gradually circularized over millions of years. Advanced civilizations might use rogue planets as natural spacecraft. Imagine discovering a rogue planet on a trajectory that will pass near your star system. With sufficient technology, you could land on it, establish a base, and ride it through interstellar space to wherever it's going. The planet provides shielding from cosmic radiation, resources for construction and fuel, and gravitational anchoring for structures. It's a ready-made interstellar vessel requiring no propulsion, just patience. The trip might take millions of years, but for a sufficiently advanced or long-lived civilization, this could be acceptable. Alternatively, if the civilization has mastered hibernation or digital consciousness, subjective time could be much shorter.
From an observational standpoint, such a planet might appear normal in most respects, but show anomalous heat signatures, radio emissions, or atmospheric chemistry indicating artificial activity. SETI programs have begun considering rogue planets as potential habitats for extraterrestrial intelligence. If we detect an anomalous rogue, one that's warmer than expected, or shows spectroscopic evidence of industrial pollutants, it might be inhabited. The search for life might need to look beyond stars into the cold darkness where rogues drift silently, some perhaps carrying passengers on journeys between the stars.
What ultimately happens to rogue planets? For billions of years, they drift, they cool, they orbit the galactic center, making one circuit every few 100 million years, passing through spiral arms, traversing regions of higher and lower stellar density. Occasionally, one passes close to a star and is captured or gravitationally scattered onto a new trajectory. Very rarely, one collides with another rogue or falls into a black hole, but mostly they drift in silence. Over trillions of years, as stars exhaust their fuel and die, the galaxy grows darker. New star formation slows and eventually ceases. By 100 trillion years from now, the last stars burn out. The universe enters the degenerate era, illuminated only by fading white dwarfs, neutron stars, and black holes. Rogue planets outlast the stars. They're already adapted to darkness. When the last star dies, rogues will still drift through the galaxy, frozen monuments to an era when light was common. Eventually, even rogue planets decay. Proton decay, if it occurs, and current theories suggest it does, will cause all matter to slowly disintegrate over timescales of 10 to the 40 years or longer. A rogue planet, given enough time, will evaporate atom by atom until nothing remains but diffuse radiation scattered across the void. But until then, for timescales that dwarf the current age of the universe, rogues will endure, silent witnesses to cosmic history.
Rogue planets challenge our notion of what makes a world significant. We think of planets as belonging to stars. Earth is our planet, orbiting our sun. We define habitability by distance from stars, measuring the habitable zone where liquid water can exist on a surface illuminated by starlight. Rogue planets upend this framework. They show that worlds can exist independently, that habitability might not require stars, that life, if it exists on rogues, might thrive in darkness we consider hostile. This expands the cosmic real estate available for life by orders of magnitude. If even 1% of rogue planets harbor subsurface life, there could be billions of inhabited worlds in the Milky Way, most of them invisible, unknown, drifting between the stars. It also suggests that our perspective is biased by our circumstances. We live on a planet orbiting a star, so we assume that's the normal state for planets, but statistically it might be the exception. Most planets might be rogues.
most potential habitats might be dark. If life is common on rogues, and if intelligence ever arises there, what would their understanding of the universe be like? They wouldn't see stars as we do, just faint points of light, unchanging, eternal. They'd have no concept of sunrise, seasons, or orbits. Their physics would be built on different observations. Their mythology would involve different stories. Would they even realize they lived on a planet? If their entire existence occurred beneath kilometers of ice, they might think their world was all that existed, an endless ocean with a ceiling of ice above and perhaps rock below, the only world in existence. The universe might contain countless such civilizations, each believing they are alone, unaware of the trillions of other worlds drifting through the same dark galaxy.
Detecting rogue planets remains one of astronomy's greatest challenges, but technology is advancing. The Nancy Grace Roman Space Telescope, scheduled to launch in 2027, will conduct microlensing surveys with unprecedented sensitivity. It will detect Earth mass rogues routinely, providing the first comprehensive census of smaller rogues. Ground-based telescopes like the Vera Rubin Observatory and the Extremely Large Telescope will contribute by detecting nearby rogues through direct imaging and astrometric perturbations, measuring how nearby rogues gravitationally affect stars' motions. Within 20 years, we might have detailed statistics: how many rogues per star, their mass distribution, their chemical composition, their ages. We might discover that certain types of planetary systems produce more rogues than others. We might find patterns in where rogues concentrate within the galaxy. We might even detect technosignatures, evidence of civilizations on rogue planets. The search for rogue planets is also a search for new worlds to study, new types of planetary systems, and potentially new forms of life existing in environments we never imagined could be habitable. Every survey, every detection, every new technique brings us closer to understanding these mysterious worlds that outnumber the planets we can see. We began this journey imagining a world without a sun, a planet in eternal darkness, frozen, silent, alone. Now we know such worlds exist, billions of them, perhaps trillions. They drift through the Milky Way, invisible passengers on journeys that last eons, remnants of violent solar system histories, or born in isolation from the beginning. Some are dead, frozen solid from surface to core. Others might harbor subsurface oceans, warmed by internal heat, potentially hosting life that will never see a star. Some might even carry civilizations, sealed beneath ice or artificial domes, traveling between stars over timescales incomprehensible to beings who measure time by sunrises. The evidence is clear. Rogue planets are not rare curiosities. They're a fundamental component of galactic structure. outnumbering the illuminated worlds we've studied for centuries. They represent a hidden majority, a dark population that challenges our understanding of planetary systems and habitability. Current missions are detecting them. Future telescopes will catalog them. Within our lifetimes, we might discover one passing through our cosmic neighborhood, a wanderer from some distant, forgotten solar system, carrying with it stories of its origin we can only guess at. The universe is full of light, stars burning across billions of light years, but it's even more full of darkness. And in that darkness drift countless worlds, each one a complete planet with geology, perhaps atmospheres, possibly moons, maybe even life. They travel alone through the endless night. No sunrise will ever warm their surfaces. No star will ever pull them into orbit again. They are truly alone. Rogue planets, orphaned from their parent stars, condemned to wander forever. Yet they persist, they endure, and they remind us that the universe is stranger, more diverse, and far more populated than we ever imagined. The darkness between stars is not empty. It is full of worlds we are only beginning to see. Close your eyes. Imagine the silence of interstellar space. Imagine a frozen world, its surface covered in nitrogen ice and carbon dioxide snow, drifting through that silence. No sound, no light, just the slow pulse of internal heat, the faint radiation of cosmic rays, and the endless forward motion through the void. Somewhere out there, right now, trillions of these worlds continue their journeys. Some have been traveling for billions of years. Some will travel for billions more. They are patient. They are eternal. And perhaps, just perhaps, we are not so different. We too travel through space on our world, orbiting a star that is itself moving through the galaxy. We are all wanderers in the cosmic dark, passengers on worlds journeying through space and time. The rogue planets remind us, in the end, we are all alone together, sharing this vast and ancient universe, each on our own path through infinity. Sweet dreams through the cosmic dark. May your journey be peaceful.